So one example that I was trying to give was that of this neural network. So suppose this is the neural network that we have. Okay, so this is the input layer and this is the output layer. Okay, so suppose output has m number of output, m cross n. Okay, so it has n number of outputs and n number of inputs. Okay, so n inputs and m outputs. Suppose that is what we have here. Okay, so if this that there is no activation, there is no bias for the timing. Let us consider very simple network. Okay, just input and output layer, no activation, no bias. It's a linear simple thing. Okay. And this is a fully connected layer. Okay, so there are weights going on here. Okay, so this is fully connected. So this fully connected this fully connected layer is something that we are looking at. Okay, so this is full connection. So outputs basically are nothing but the linear combinations of all the inputs. That's all we have, right? So suppose W is the weight matrix. So suppose W is the weight matrix, then what do we really have? So suppose Y is the output and X is the input. If that is what you have, then Y, which is a vector in Rm, M, and X, which is a vector in Rn. Okay, and what does this weight matrix W is? So the weight matrix W is Y is equal to Wx, right? So Y is equal to Wx. So what is the size of the weight matrix here? In this particular case, the size of the weight matrix is Rm cross N, right? Rm cross N, and here you can see this weight matrix is taking a input of size N and transforming into the output of size W, right? And this is how you get your the outputs, right? So Y1, for example, is equal to W11 X1 plus W12 X2 plus so on so forth plus W1N Xn, right? That is what you have. So this is your Y1 and this is suppose X1, X2 and so on and so forth. Then this weight is what is W11. Then you have X2 going to X1. So this weight is W12 and so on and so forth, right? So this is W12 and so on and so forth. So all the weights going to 1. So this is the notation that we are looking at, and with this notation you see that this is what you will get. Right, so you will have W11 X1, W12 X2, and it's like an adder here. You add all these things together and you get Y1, right? And then in a standard neural network, what do you have here is an activation function. So something like ReLU. So you will decide the sign of Y1, say for example, whether Y1 is greater than 0 or less than 0. Depending on that, you will decide whether Y1 remains Y1 or Y1 becomes 0, or there is that inverse tan tan hyperbolic, all those different types of non-linearities, sigmoid that you can think of there, right? And then there is a bias term added. So that is one standard layer. So in that standard layer, I'm just focusing on to this particular part. Okay, so now suppose inputs are given to you, several instances are input are given to you, and corresponding several instances of output are given to you. Then basically Y is equal to Wx. So you have a functional relationship between Y and X. And what do you really want to do when you are trying to train a neural network is trying to decipher this functional relationship. This is very much similar to the least squares problem that we have seen, right? There is a functional relationship. You are trying to decipher the functional relationship. In least squares problem, what did we find out? In least squares problem, we found out the coordinates of the basis functions, right? So that's what we found out. So here, what we will find out? Here we will find out best possible weights, right? So in a neural network, when you are training a network, what you are really trying to do is you are trying to find out best possible weights. Okay, and what do you do with these best possible weights? The best possible weights are found out in such a way that the predicted output matches as closely with the observed output, right, in the training phase. That's what you're doing. So weights are actually trained. That means that you are actually solving an optimization problem. So the optimization problem cost is something which is gauging, or which is kind of quantifying how good the fit is, right? So that is called as loss function. and you have that loss function, and with respect to the loss, you kind of train the weights, right? So that's what you are basically doing. So this is what you have. So weights are to be trained, and weights are basically like decision variables in the optimization problem that you are trying to solve. So obviously, if you have a fully connected layer, if you have a fully connected layer like the one I have shown here, where there are n inputs and m outputs, then there are total mn number of weights, right? Total number of weights, total number of weights is mn, right? So total number of weights is mn number of weights are need to be trained, right? So based on the available data sets that you have to train total mn number of weights. So sometimes you don't want to train too many number of weights, sometimes you don't want to do that. There are a lot of reasons why you don't want to do that, so I'll not get into that. But what I will do is the following. Okay, what I will do is the following. So this is a fully connected layer that I have. Now what I do is that I have this m input sitting over here. So these are these m inputs. Okay, x, right? So x is a vector, input vector is in Rm, right? So this is what I have. This is the input layer. So this is the output layer that I have. Okay, so this is y in R m, right? So input was m, okay, n. So this is Rn. So this is the output layer. And what do I do between this input and output layer is I introduce a hidden layer. Okay. So there are how many guys in the hidden layer? So this is the hidden layer that I find out. And in this hidden layer, there are R number of entries. Okay. So the hidden layer has R number of elements. So here you have N. So there are R nodes in the hidden layer. Okay, so this is what you have. And now what do? I do a fully connected network on these layers. Okay, I do fully connected network on these layers. So there are connections here like these, and then there are connections here like these, right? So here these connections are there, and from here you have these type of connections, right? So this is what you do. So there is a fully connected layer between input to hidden layer and from hidden to output layer. Okay, so here also I'm not worried about activation. I'm not worried about bias. I don't have any activation or bias in the hidden layer as well. Okay, so this is the connection that I do. Then suppose this hidden layer, if I call this to be edge, right? So how is the input output relationship now really going to work? So suppose this part I will call W1 weight matrix, and this part I'll call W2 weight matrix. Then clearly H is a vector in RR, X is a vector in Rn, and y is a vector in Rm, right? So this is input and output we have fixed exactly same as what we had in this previous architecture. But now I have a hidden layer introduced in between. And because of this hidden layer that I have introduced, what do I have? H, X and Y, right? So I have these. And now in this first layer from input to hidden layer, how is the relationship given? The relationship is given in this particular format. H is equal to W1X, right? And now in the hidden layer to output layer, what is the relationship? The relationship is y is equal to W2H, right? So what is the relationship that I have? I have W2 W1X. And what are the sizes of matrices W1 W2? So W1 is now what is the size of W1 now? The W1 is now Rn cross R. Is that correct? And W2 is now R cross N. Is that okay? These are the sizes of W1 and W2, and this is the relationship that I have. Y is equal to W2 W1X, right? Previously, what was the relationship that I had? The previous relationship was Y is equal to WX. Here the relationship is Y is equal to W2 W1 WX, right? So now once I have this, what is the objective again? The objective again is to train the weights, but now the weights are in form of W1 and W2. So I'll train the weights. I'll train the weights W1, W2, and after training the weights, what is the objective? The objective is that the predicted values of Y match as closely with the observed values of Y as possible. Is that okay? Does that make sense?
Sir, W1 should be R cross N or N cross R.
W1 is, sorry, N cross R cross N. You're right.
And similarly, W2 should be N cross R.
Yeah, N cross R. You're absolutely right. You're absolutely right. So in the notation that I'm using here today, in that notation, these are the size of the matrices. Thank you. So does that make sense? What I have done here, does that make sense? Is that okay?
Yes, sir.
Yeah. So if what I have done here on this page and what I have done here on this page makes sense, what is happening with the weight W or the weight matrices W1 and W2? So by introducing the hidden layer, have I increased the number of weights? So how many weights I was training here in this particular fully connected single layer neural network? How many number of weights I was training? I was training mn number of weights, right? So here, how many number of weights I am training?
R times m plus n.
R times m plus n, right? So I'm training R times m. So by introducing a hidden layer between these two input output layers, what have I achieved? Have I achieved reduction in number of weights that are trained, or have I increased the number of weights that I am going to train?
Reduced.
We have reduced. Okay, so we have reduced. So if this second architecture that we are seeing on this slide, if this also gives acceptable prediction performance, like the loss that we have in both the cases, the loss was same. So if the loss that we get here is acceptable loss, which network we would use? Possibly we would use this network because you have to train less number of weights here, and still you get the same performance that you are getting in this particular slide. Does that make sense?
Yes, sir.
Yeah. So now if that makes sense, so if you see that the prediction performance here in the single layer network or prediction performance here in the hidden layer, that is two layer neural network, if both the prediction performances are same, comparable, we will assume that they both are same, suppose, then what is the relationship between W and W2 W1? What might be the relationship between W and W2 W1?
W equal to W to W1.
W equal to W to W1. So it may not be exactly equal because these prediction performances may not be exactly equal, but they are comparable. So what we know, so let us call this prediction here. So I will call this prediction, let us say Y2, the second architecture. And this particular prediction, I say Y1 from the first architecture. What I am saying is Y1 is roughly equal to Y2. Okay, so Y1 is equal to Y2. Okay, that is what we have. So W is basically roughly equal to W2 W1. That is what you are basically saying. Is that okay? So what you are basically doing is you are looking. So what is the rank of W now and what is the rank of W to W1? So roughly, like generically, like we had discussed, this rank might be actually the minimum of Mn, right? But here the rank will be R, and if you chose R to be strictly less than minimum of Mn, okay, then you have a smaller rank. What are the advantages? So the product W to W1, the product W to W1 is actually, the product W to W1 is actually a very interesting thing. What it is doing, this product W to W1 is trying to approximate the original weight matrix W, right? With less number of parameters. What are the parameters? The trainable weights. So the number of weights is less. You have reduced the number of weights, still you achieve the acceptable prediction performance, right? The prediction y1 is approximately equal to y2. So what you are really doing is that in this architecture, whatever weights you would have obtained, trained weights, what you are really doing by introducing a hidden layer in between is like you are looking at a low rank approximation of the matrix W. You are trying to find out best R rank approximation of the matrix W such that your prediction performance is not really very bad. So this is something that is really very interesting, because if you have your input layer is exactly same as output layer. Okay, so what you really do is that whatever input you give, your output is exactly same as input. Y is equal to X. Then what you really are doing by introducing this hidden layer, like all the conditions that we have is that activation is not present and so on and so forth. Bias is not present, say for example, or you can have bias. You can prove later on then that bias has some relationships. So what you are basically doing at this is these type of neural networks where input is same as output. They are called as auto encoders. And if you have linear auto encoder, then what you essentially are doing is principal component analysis. And that principal component analysis anyway is kind of low rank approximation, right? So that is the connection. That is the connection between these training neural networks. So this is probably at a higher level. I am doing too much of hand waving here. I have given too much of information quickly without writing much, but I just want you to kind of get exposed to this type of work. Okay, so this is where linear algebra and these deep learning or autoencoders, they are very nicely intricately related with each other. Okay, so what is really happening here? What is really happening here is that you are looking at a low rank approximation, and through low rank approximation of this weight matrix, you are actually trying to optimally train your neural network. Okay, so the same thing applies for tensors also. So for example, you have input as a vector, output is also a vector. But if you have input as a tensor and output is also tensor, then instead of having a weight matrix in between, you have a weight tensor, and you do decomposition, low rank approximation of that weight tensor to optimally train the deep network. Okay, so these are the type of research works that are currently going on. People are trying to investigate, especially in case of video and image analytics, these type of decompositions, low rank approximations of matrices and tensors, and how would they be really very useful in training a deep network. Okay, so that is something that people are trying to look at. So there are some very interesting research papers in recent past, like in last 5-6 years, there have been very good, very interesting research papers where these type of approaches have been invoked in order to train a deep network efficiently. Okay, so something like this is really very important. So low rank approximations, you might seem it's a far-fetched mathematical fantasy, like I like to teach, so I'm teaching. So it's not really like that. It really has very interesting applications. One of the important applications which is related to deep learning is basically this. Okay, so this is something I just wanted to draw your attention towards. And another particular case of this is that when input is same as output in the neural network, then such neural networks are autoencoders. And if you have a linear autoencoder, then what you essentially are doing is principal component analysis. This again has been proven mathematically very nicely in papers. So this is something that people have been exploring for a long time. So about 25-30 years ago, people established this connection of principal component analysis with this autoencoders. Okay, so since that time, as recently as 2017, 2018, up to that time, people have been writing papers about these things where they're trying to see the connections, they're trying to come up with better learning algorithms, and hence try to compute PCA or the other way around. See how these things are really theoretically equivalent to obtaining principal component analysis of weight matrix and so on and so forth. Okay, so these are the type of things that are really very interesting, and they are current active areas of research. Because I am not talking too much of loss function formally, and because I am not talking of these optimization algorithms that are involved in training the weights, I am not really going in details about showing how this is really a low rank approximation and so on and so forth. But this is something that exists. Okay, so I'm doing a lot of hand waving here, but I want you to appreciate that whatever we have learned is like really a topic of interest, and people are actually using these type of things in very current research, right? So this is something that is really very important. I possibly I will share a couple of research papers, a couple of papers which kind of demonstrate this. Okay, so this is something that I will possibly share with you, so you can look, and those who are interested can pursue this further. So this is something that I just wanted to draw your attention to. So is this kind of the general bird's eye view? Overall picture is clear. I am not expecting you to understand all technical details here in one go. Not that I have explained them properly also, I accept, but this is something like kind of passing on information. Okay, so like low rank approximations we have done in detail. Where are they applied? This is one place where they are applied. So is this part like kind of clear? Do you have any comment to add, or your previous experience in this if you want to share? Anybody? So has anybody ever used these type of techniques to train neural network, or have you any time before came across these type of things? Any of you? Do you have any experience to share about these things?
Yes, sir. We have done, but probably at that time we did not realize that the hidden layer is actually doing that. I mean, it's probably the first principal components.
Yeah, in autoencoders. Okay, not in case of,
yes.
in autoencoders. So there also in the hidden layer, what is really happening is that how many number of neurons you have in that hidden layer, how many number of those nodes you have in the hidden layer, that determines what you are really computing. So if you have R number of nodes in between, R number of neurons in between, which are in the hidden layer, then what you really get is the R dimensional principal component subspace. You do not really get principal components specifically, but you get the span of those principal components, which is called as principal subspace. Okay, so that is what you really get in your output. When you train the network, that is what you will get in your output. If you have only one neuron in the hidden layer, then what you get is the first principal component exactly, because the space that it will span is also one-dimensional space. The problem with the multiple neurons in the hidden layer is that if you have more than one, say for example 2, then what really happens is that you get the span of two-dimensional space. Any orthogonal basis in that two-dimensional space will serve the purpose, right? So there is some issue with that. That's why, as far as uniqueness of PCA is concerned, this architecture, if you have R greater than equal to 2, you will get principal component space rather than principal components. So it's like getting almost principal components. Some extra work needs to be done after that. But if you just have R is equal to one neuron in the hidden layer, then you get exactly the first principal component after training the weights. That's what would happen. Okay.
Yeah. Thank you, sir.
Yeah. Anybody else who want to say something?
Hello, sir.
Yes. Ashraf, yes.
Sir, I once read a paper on tensor decomposition and deep learning, So they had initially, let's say, a 10-layer network, and they trained it for some number of iterations. And after that, they performed tensor decomposition in each layer.
Correct.
And after that, they the decomposed network, they again trained it for some iteration. So
Correct.
this low rank approximated network achieved
Yeah.
almost same accuracy as the original network with much less weight.
Correct. Absolutely. Yeah, that's right. So that's what is really going to happen. So these are the type of papers that you have mentioned. These are the type of papers like fairly recent papers which are employing these type of techniques to kind of train the deep networks. So this is something that is like really very interesting and active area of research. So yeah, thanks. Yeah, you are right. Anybody else who has any like past experience want to share, or some very interesting paper or book or place where you had read these things written very nicely? Please feel free to share these things. Like everybody, including me, will get benefit out of it. Okay, so please feel free to share right now if you want to. Okay, in that case, we can go further and see another example where these low rank approximations really come helpful. But this example is an example where we are not going to look at low rank approximation, but we are going to look at something which is much more than a low rank approximation. Okay, so first let us see what we are going to do. So suppose I have, let us say, this y1, y2, y3 a time series. Okay, I have a time series. Okay, so in this time series, what is going to happen? Okay, in this time series, what is going to happen? Y1, y2, y3, y4, and so on, so forth. Okay. So suppose in this time series, the time series is such that it has auto-regressive nature. So what is the auto-regressive nature basically of the time series? The auto-regressive nature of the time series basically is that suppose y4 can be written as linear combination of previous three instances. Okay, so y4 I can write down as alpha 1 y1 plus alpha 2 y2 plus alpha 3 y3. Okay, this is what I can write down. Y5 I can write down as alpha 1 y2 plus alpha 2 y3 plus alpha 3 y4 and so on and so forth. Do you understand? So this is what I can write down. So every observation in the time series actually depends on past three instances, past three time instances, and you can actually exactly know what is y3, what is y4, y5, y6, y7, and so on and so forth. Okay. So if that is the case, then I look at a particularly interesting matrix. Okay, y1, y2, y3, y4, y5, y6. Okay, let us say. Then I look at y2, y3, y4, y5, y6, y7. Okay. Then what I do? I look at y3, y4, y5, y6, y7, y8. Then what do I do? I do y4, y5, y6, y7, y8, y9. Do you get hang of what I am really doing here? Do you see how am I arranging the entries of this particular matrix? Is that okay? Do you see how I'm constructing the matrix like this? So this particular matrix is called as Hankel matrix. Okay, this particular matrix is called as Hankel matrix. Okay, so y9, so y5, y6, and so on and so forth. y6, y7, and so on and so forth. So suppose y6, y7, y8, y9, y10, and y11. Okay, so 1, 2, 3, 4, 5, 6, 6 by 6. So I have only 11 observations, let us say, in the time series. All those 11 observations I write in this particular way. Okay. So this is a Hankel matrix, which is of the size 6 by 6. Correct? This is a Hankel matrix. So this particular spatial structure, what is the spatial structure that you see here? You look at these. Okay, so this is y1, so this is y2, these elements are y3, these elements are y4, and so on and so forth. So these are kind of anti-diagonals, if you want to say, and all the anti-diagonal elements are basically the same. Can you see that? That's the spatial structure that we observe in this particular matrix. So look at this particular matrix carefully. Look at this particular matrix carefully. In this matrix, can you tell me spatial property of this matrix, if you can? Does this matrix have some special property here in this particular case, given that this is the relationship that you observe in y1, y2, y11, right? So this is the relationship if you observe in these yi's, all of them, then can you say something about this matrix? Looking at this matrix, what can you say?
So symmetric matrix.
It's a symmetric matrix, that's right. But much more than that, it's a symmetric, obviously it's a symmetric, you are absolutely right. But more than that, what can you say?
Sir, each row is left permutation of the previous row.
Correct. That is the way I have arranged it, right? That's why I get that anti-diagonal structure. That's also okay. But more than that, what it is? Can you say something about rank of this matrix? What do you think should be the rank of this matrix?
It is going to be full rank.
It should be a full rank matrix. Why do you think it should be a full rank matrix?
Basically, like, because we are shifting one permutation at a time,
Hmm.
now the linear combination has one new element. Like every linear combination is just off by one element. So that makes every linear combination independent of each other.
So what do you think the rank of matrix should be?
It should be full rank. Like every row is
6.
independent of each other.
Okay. So Kshitish thinks that the rank of this matrix should be full. I say you observe the following. You consider this first column, multiply first column by alpha 1 into first column. Okay. Okay, so there is some problem with this. Let me restart again. I hope it is okay. Okay. So you think of it. You look at the first column. First column of this matrix, multiply the first column, I would say with C1. Okay, multiply the first column with alpha 1, multiply second column with alpha 2, multiply third column with alpha 3, and add them up together. What would you get?
Fourth column.
You'll get the fourth column. So you have fourth column written as linear combination of first 3 columns. So can the rank be 6?
No.
The rank cannot be 6. So rank can be at most 5 from this logic. Now extend this logic further, and can you tell me what might be the rank of this matrix?
So 3.
Correct. So the rank of this matrix looks like has to be 3. right? And why is the rank 3? The rank is 3 because of this autoregressive relationship in the time series that I have stated. So basically, what is this called? This is something really very interesting. So suppose this 3. So okay, so there are past 3 instances. Okay, so the current observation in the time series is dependent. Current observation in the time series is dependent on past 3 time instant observations. Okay, so that past 3 time instant observation, so that 3 is called as order of the autoregressive model. Okay, so that order of the autoregressive model actually is same as rank of this Hankel matrix. So order of the autoregressive model is actually equal to rank of this Hankel matrix that we have constructed. Do you see the connection between rank and the order of this autoregressive model? Are you all sure? Like, do you all understand what I did? I took alpha 1 into first column, but alpha 2 into second column plus alpha 3 into third column, and I get the fourth column. Is that okay? That's perfectly clear, right? But now in real life, what is going to happen? In real life, what is going to happen is that all these observations, even if there is exact linear autoregressive model present in the data, what is going to happen? What is really going to happen is that there is some noise term that is going to get added every time, right? So there is some noise term that is going to get added, and this noise term we are not able to exactly know what it is. It's a random thing. So rather than this y1, y2, y3, y4 that you see in this matrix, what we are going to observe is y1 tilde, y2 tilde, y3 tilde, y4 tilde, y6 tilde, and so on and so forth. All these observations are going to get added by certain noise, right? All these observations are going to get added by certain noise. And we saw that if you have a low rank matrix and you add a very small noise or very small perturbation to this low rank matrix, the perturb matrix almost always will be a full rank matrix. Do you remember that discussion we had last week sometime about low rank matrices and how the nature of low rank matrices is? So you have a low rank matrix, you added a small perturbation to it, and what happened? You got a full rank matrix. So because you observe a time series data, even if the time series is autoregressive, you observe the data with noise. So the Hankel matrix that you construct, because of noise, how much ever small it is, will be a full rank matrix. But now we understand singular value decomposition. So you check the singular values of this Hankel matrix, and indeed, if the rank of this Hankel matrix is 3, or in other words, if the order of this autoregressive model were 3, you will see that you have 3 dominant singular values, and the other 3 singular values here in this 3 by 3 matrix, the other 3 singular values will be comparatively smaller than the first 3 dominant singular values. Do you understand what I'm saying here? Is this part clear? Are you following what I'm saying, or you want some more explanation? So what we are actually looking at is a Hankel matrix, and what we want to find out, what we want to do in order to decipher if there is an autoregressive relationship in the given time series or not, we can find out the nearest low rank approximation to the Hankel matrix. Now, the problem in computing the nearest low rank approximation is that the Hankel structure in that low rank approximation may not be preserved. Okay, so if you can find out a low rank approximation, of rank 3 such that the Hankel structure is also preserved, then what we really have is a cleaned time series or noiseless time series, or the time series, that part, that component which is exactly the autoregressive part. Okay, so that is what you will get. So you will actually be able to decipher what is the relationship, what is the autoregressive relationship, and not only that, you will be able to kind of get the denoised time series or denoised time series observations from this low rank approximation. But the low rank approximation that you will be requiring will be structured low rank approximation. Okay, so this structured low rank approximation. So this structured low rank approximation that you see, so this structure is that the low rank approximation should have Hankel structure on top of it being a low rank approximation. Okay, so that is something that is really very critical. Unless the structure is Hankel, you cannot go back to the time series. You cannot go back to the time series idea. Okay, so that is something that is really very important. So that is what I wanted to say. So this is another application of low rank approximation, and not only low rank, a special case of low rank approximation which is called a structured low rank approximation. Okay, and the structure word comes because you are starting with a specially structured matrix, here in this particular case Hankel matrix. Okay, so this is one instance. This is another instance where these low rank approximations are really very useful, and especially these low rank approximations of Hankel matrices, they are really very important in this obviously statistics. So statistics, especially in this time series data. Okay, so this is where these Hankel structured low rank approximations are really very important. Another important area where these low rank approximations of Hankel structured matrices are important is in systems theory or in control theory. Okay, so in control theory, people do get control theory. People do get this input output data from the state space model, and they want to find out the order of the model. Okay, so that order of the model is very similar to this auto-regressive order of the time series data, and that order of the model that they want to find out, they have exact same idea. So this control theory they also build something which is called as Hankel matrix from input output data, and from that input output data they try to find out the rank of Hankel matrix, determining the order of the model. Okay, and people like to work with low order models because they are easy to handle computationally. The same reason why in a time series data also you want an auto-regressive model, it's a low order model. So people always want to do that. Okay, so this is something that is really very important. So this type of low rank approximations have been around for a long time. In fact, in control theory, probably as early as 1970s. Okay, as early as 1970s. 1970s, people realized that this is true. So like one of the greatest control theorist called Thomas Kailath, okay, in his book, so he's a professor in Stanford. Probably is retired now, but he was a professor in Stanford University, and one of the like prominent figures who wrote a wonderful book in linear control theory, okay, linear systems theory, and has been a textbook for almost all these 40 years, 50 years that he has written this book. So in his book, in passing, he just makes a comment that, you know, you have this Hankel matrix, find a structured low rank approximation of this Hankel matrix and we will get the lower ordered system and so on and so forth. Okay, so since then people have been talking of these low rank approximations, Hankel low rank approximations. Even today people try to come up with this. So this is one of the very important problems computationally also, because this low rank approximation, there is no closed form solution. Like for any matrix, you can use singular value decomposition and you get exact expressions for a low rank matrix. Here singular value decomposition does not work because it will destroy the structure. Okay, so if you have the singular value decomposition of a matrix, so suppose A is a given matrix and you do singular value decomposition U sigma V transpose. Okay, and then you just pick sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose plus sigma 3 U3 V3 transpose. Okay, so this is the matrix that you picked, which is A tilde. Then there is no guarantee that if A is a Hankel matrix, then A tilde is a Hankel matrix too. There is no guarantee. The only guarantee that you can take is that A is a symmetric matrix, then A tilde is also a symmetric matrix, because for a symmetric matrix, a singular value decomposition looks like this. U sigma U transpose. Okay, so because of symmetry, it looks like this. And once you have this structure, then you have sigma 1 U1 transpose plus sigma 2 U2 transpose. Then obviously low rank approximation that you opted from SVD for a symmetric matrix is symmetric, but a Hankel matrix you start with. So this is the Hankel matrix that you started with. You find out singular value decomposition U sigma V transpose. You just forget the 3 singular values which were not dominant and only consider the dominant first 3 singular values corresponding to the order of the model. Then this A tilde that you get, there is no guarantee that this A tilde will be a Hankel matrix. And how to compute a matrix which is nearest low rank Hankel matrix to a given Hankel matrix. This problem is still an open problem. How to solve this optimization problem, not very clear. People try various approaches. There is a lot of progress in this area, but the closed form guaranteed solution to this highly nonlinear optimization problem still does not exist. Okay, and then there are other structures which are much more difficult and interesting than this Hankel structure, like Toeplitz structure. So these are the type of structures which are really very important. So these type of structures also come into the picture. A lot of things like image deblurring, for example, is something as an application of a low rank approximation, structured low rank approximation, with the structure being Toeplitz. Okay, Toeplitz matrix. So it's a displacement kind of structure, resultant matrix structure. So that is what people have been working on. So this low rank approximation problem computationally still is not tractable when you have an additional constraint that the structure should be preserved. Okay, so for example, Hankel matrix low rank approximation, or say Toeplitz structured low rank approximation. These are the type of problems which are not settled fully in the literature yet, but they still have a lot of application. People are trying to come up with advanced computational techniques to address these problems. Okay, so this is something that is really very interesting. So time series data, I think, is much more appealing as far as the course is concerned. The least squares problems and everything you know already. So that's why I tried to put this connection of low rank Hankel matrix with this time series data. So this is another area of research, active area of research, especially in statistics these days, where people actually try to find out low rank approximation of Hankel matrix and use them in time series data analysis. Okay, so this is something that is really very useful. So this is another area where these low rank approximations of matrices actually play a very important role. So this is something that I wanted to point your attention to. Again, a lot of hand waving I have done. These are difficult problems and cannot be covered in 3-4 lectures easily. So I'm just pointing you towards these different areas that you can explore if you are interested in applications of low rank approximations. Okay, so this is another area that you have seen. The third area, of course, is, I think, very probably done in detail by Professor Adhay, which is principal component analysis. So principal component analysis is another way, another approach where low rank approximation of matrices actually is important. Okay, so these are the 3 important areas in which low rank approximation of matrices is important. I wanted to kind of draw your attention towards these 3 application areas. So like anybody who has worked in this type of work or signals and systems before, anybody who is like electrical engineer who might have used this, or a statistician who have used these type of time series data and constructed these type of matrices. If you have any past experiences, or if you are aware of any such related work, please, if you want to share, you feel free to share now. This is another area where these things are applied. If you have any doubt or want to ask anything, please feel free to ask.
Sir, I have a question.
Yes.
Sir, so as you said, a symmetric matrix, for a symmetric matrix, the singular value decomposition will be U sigma U transpose.
Yeah.
So this is something like, if we just try to intuitively understand,
yeah,
it kind of means that the V vector, when it is operated by A, it does not get rotated. Probably it only gets stretched.
Yeah.
But then that happens only in orthogonal matrix, that it
No.
will not rotate it. But
No,
how
no.
can it happen in symmetric?
No.
Yeah.
So for a symmetric matrix, you see this is the form of singular value decomposition, right? Because of the symmetry of the matrix A, you have A is equal to A transpose, right? You have A is equal to A transpose. That relationship needs to be satisfied by the singular value decomposition also, right? So the transpose of this matrix should be itself, no? So V transpose is V sigma transpose, and you should have this, right? So U transpose, that's what you have, and these two things should match basically. So this thing should match with this thing. So if that is to be matched, then you can use the properties of matrices, and in fact you can show that that you will get singular value decomposition of A in this particular type. Okay, this is the singular value decomposition of A, where this sigma actually is the square of eigenvalues. That is something that we have already seen. So a square root. Okay, so this is something that has to be understood properly. But if you can write down the equations, then you will see that this is going to happen. And now this U sigma U transpose you can write down as U1 transpose plus sigma 2 U2 transpose, and so on and so forth, right? So U1 transpose is a matrix of rank 1. This will be a symmetric matrix because U1 transpose you are writing, right? So U1 transpose will be U1 transpose U1 transpose, which is nothing but U1 transpose. So that means that U1 transpose is a symmetric matrix of rank 1. And then you add these three symmetric matrices of rank 1. So sigma 1 U1 transpose plus sigma 2 U2 transpose plus sigma 3 U3 transpose. So these are the three rank 1 symmetric matrices you add. You will get a symmetric matrix again, which is nothing but A tilde, which is the low rank approximation of A. So for a symmetric matrix, low rank approximation by singular value decomposition will always be symmetric, but much more than that, like a structure like Hankel, you cannot guarantee. You will not see that. Is that okay, Kaushik?
Yes, sir. Sir, I mean,
yeah.
Probably I'm still trying to understand about that rotation, which I was thinking about that.
No, so don't. Okay, you think about it. If you still are not sure, we can discuss this again tomorrow. But you see, this is very closely related to eigenvalue, eigenvector decomposition also. So you think of it from that point of view also, that is fine. You will see the relationship actually. You can decipher the relationship on your own.
Sure. Thank you.
Yeah, and if it is still not clear, we can discuss it tomorrow. But you are right, you can go in that direction also. And if you are thinking in that direction, that's also fine. Okay, so that's okay.
Thank you, sir.
Any other thing? So let me just see if I can help you with this. So any other doubt, any other comment if you want to have? Okay, in that case, let me stop sharing this and let me share another screen, and let us see if I can help you with what you are trying to say. Okay, so let me share another screen. Just give me a minute. Okay, so now my screen is visible, right? So I'll randomly generate a 6 by 6 matrix. So this is a 6 by 6 random matrix I have generated. So what I will do is I will have A plus A transpose. Okay, so if I do A plus A transpose, you see I will get a symmetric matrix now. Why? See, this entry is same as this entry, right? So this is the diagonal entry. This entry is same as this entry. You can very easily see A plus A transpose is a symmetric matrix, right? So I have constructed a symmetric matrix. So this is the symmetric matrix that I have constructed. Okay. So let us see what is the singular value decomposition of this symmetric matrix. So USV is SVD of A. Okay, I'll do SVD of A. So SVD of A, you see, these are the U and V matrices. Okay, so especially if you want to see what is happening with U and V, you can check U and V. Okay, so if I want to print them, let us see. Okay, so 1, 2, 3, 4, 5, 6 U and V. I hope they will come in the in one line. So can you see this? So if you see the first, so U matrix, so the first 6 columns are U matrix, the next 6 columns are V matrix. You can see they are same, possibly for a sign, right? So the sign here is you have this particular minus plus, right? Exactly plus minus different, possibly, but that you can adjust in the eigen values. Okay, so singular values, that's not a problem. So this is what you will get. Is that okay? U and V, do you see? They're exactly same matrices, possibly for a sign difference. Huh? And now, I think the command to find out eigenvalue, eigenvectors is so. If I remember correctly, then IG A. Okay, so it will give me eigenvalue, eigenvector decomposition. Yeah, so it will give me eigenvalue, eigenvector decomposition of A. And you look at the eigenvalue, eigenvector decomposition. What is the most dominant eigenvalue here? 6.9662. What is the singular value here? 6.9662. What is the singular vector corresponding to this singular value? The singular vector corresponding to this singular value was minus 0.455. So all the signs are negative. All the signs are negative. Or here, what is the vector that you see here corresponding to this? Is it the same vector except for the sign difference? So you can see this vector and this vector. They're same except for the sign difference. Kaushik, can you see?
Yes,
that?
sir. They're same. Yeah.
Yeah. And now take this analogy forward. Okay, take this analogy forward and try to see what is happening with the eigenvalue, eigenvector decomposition of a symmetric matrix, and what is happening with the singular value decomposition of the same matrix, and why you should get a symmetric U sigma U transpose type of singular value decomposition always for this. You can now figure it out on your own easily. You understand that,
Sure.
right? You saw this.
Yes, sir. Sure.
Now you can just write down the equation, and you can use the theoretical this thing, right? If U sigma V transpose is the singular value decomposition of A, then you know what is the singular value decomposition of A transpose. Then you can calculate what is A transpose, and you can calculate what is A transpose A, correct? And whatever you get, they are actually the singular value of eigenvalue, eigenvector decompositions from spectral decomposition theorem, and then that relation you can use. So I think this you can decipher possibly by your own. Give it a try. Otherwise, I'll once again try to.
Sure, sir.
But this you saw yourself, right? I generated a random matrix For a random matrix, I constructed a random symmetric matrix. For that symmetric matrix, we just computed SVD. We just computed eigenvalue, eigenvector decomposition, and we are seeing this. Okay, so try to see these connections. It's very important. And then this will tell you that, okay, so the question is singular value decomposition, right? So I am overshooting time. Those who have other class may join the other class. I'll just take 2-3 more minutes, not more than that. Okay, so this is your SVD. And in the SVD, you see this is the smallest singular value, 0.1114, right? So this is the smallest singular value that you have. So what I will do is I'll set this singular value to 0. I'll set this singular value to 0. And if I set this singular value to 0, then I'll get a rank 5 approximation of the given symmetric matrix, right? So let me do that. So S66. Okay, so let me do this. S66 I'll set to 0. So if I set this S66 to 0, how does this matrix look like? You see the last singular value has been opted to be 0. Okay, so now I don't remember in MATLAB whether the SVD is written as U sigma V transpose or U sigma V, but let us try. Okay, so U star S star V transpose. Okay, so U S V transpose. So U S V transpose, you see this is the matrix that you get. And what was the original matrix A that you started with? So A was A plus A transpose. So you see this is the matrix that I have. This is the matrix that I have, which is USV transpose. So this matrix, I have this. The rank of this matrix will be obviously 5. And this matrix A you see here was the original matrix. I obtained this matrix from, so you see all the entries here, all the entries here are slightly perturbed. Not only that, you see that this matrix that I have obtained, U sigma V transpose, the low rank approximation, this is a symmetric matrix also, but that is something that we expected anyway from theory, right? So you see all these entries here, they are all symmetric, right? So you have a reflection around this diagonal. You see all these entries, this matrix is symmetric matrix. Is that okay? So this matrix is symmetric matrix. One more simple thing, now that you have done all these things, you can check what is the norm of this matrix A minus USV transpose. What do you think should be this norm? What should be this norm? What should be the answer here?
Singular value which we deleted.
Correct. Singular value which we deleted. So what was that? That was 1114. Correct. So this is the singular value which we made 0. You remember? So here you see where somewhere this is the singular value that we had, 1114. So that is the distance. So you see this is the distance, right? So you have found out a low rank approximation. This is your low rank approximation. This is also symmetric because the matrix that you started with is A, that is also symmetric. And you look at the difference between these two matrices, the norm difference actually is 0.1114, which is something that you expected, you wanted anyway. You knew theoretically that this is what is the answer, and you can actually see it from this simple simulation also that actually is true. Okay, so these are few types. So these are few things that you can actually look at. Okay, so yeah, anything?
Sir, but the matrix. Okay, the matrix A has the first top left and the bottom right has different values.
Which matrix?
The matrix A.
Yeah, the one that you are seeing right now here.
Okay,
I'm pointing.
sorry. Got it, sir.
Okay, fine. Okay, fine. And let me just see if I can like do one more thing. Hankel. Does it? Okay, I forgot the command for Hankel matrix generation. So no, so I don't know how, like I forgot, otherwise I would have demonstrated how Hankel matrix and its SVD, it will not match. I would have shown, but I forgot how it is done. So maybe what I will do is 1 minus 1 3, 4, minus 1, 3, 4, 0, 3, 4, 0, minus 2. So how many rows I have written? 3, 4, 0, minus 2, 1. Okay, so this is the matrix I have written. Is this the Hankel? Does this matrix have Hankel structure? Okay, this matrix has a Hankel structure, right? Let us check what is the rank of this matrix. So the rank of this Hankel matrix is a 4. Okay, so let us check what is the singular value decomposition. Okay, so I will rewrite previous USV. Okay, so USV is equal to SVD of this Hankel matrix H. Okay, so I will compute singular value decomposition. What are the singular values? 6, 6, 5 and 0.134. Okay, so this singular value that you see here, the smallest singular value is comparatively smaller than the 3 singular values that you have. It's not very small, but it is comparatively smaller. Okay, and you can check once again, because the Hankel matrix is also symmetric matrix. You check the columns. You check the columns here, except for the sign, they are same. Okay, the columns of U and V, except for the sign, they are same. So now what I will do, I will construct a new matrix. I'll call TH. And how do I construct it? So first of all, what I'll do, I will put S44 to 0. Okay, so I'll put S44 to 0. So what does that mean? The smallest singular value I have made it to 0. Now I will construct H tilde to be the new matrix, which is USV transpose. Okay, so if I have this H tilde USV transpose, you see this matrix is symmetric, but this matrix is not Hankel now. I have found out the nearest flow rank approximation to H, right? So what is the matrix H? This was my original matrix H. 1, minus 1, 3, 4, minus 1, 3, 4, 0. So you see this matrix H is a Hankel matrix. You see the anti-diagonal, they are all like same. So this was a Hankel matrix that I started with. I use singular value decomposition. I use the singular value decomposition to find out the nearest low rank matrix. I get a symmetric matrix, all right. Okay, so this is symmetric matrix. You see the low rank approximation, I get symmetric matrix, all right. 2.957 is 2.957, but this entry is not same as these two entries, right? If it were to be a Hankel matrix, I want this entry also to be same as the two entries that are there on the anti-diagonal. But that does not happen, unfortunately. It's a symmetric matrix. It's not Hankel matrix. So this particular matrix, I cannot attach time series what you say interpretation, right? Here I know that this is the first term of the time series, second term of the time series, third term, fourth term. Then I know that this is fifth, sixth and seventh term. But because here I cannot do that, because these entries do not have this particular very nice Hankel structure. That's the problem that we have here. So ideally what I would have wanted, a Hankel structure here, but I do not get such a Hankel structure just using SVD. That's the point that I'm trying to make. So additional constraint of structure is something that is a difficult constraint. It makes this problem of low rank approximation really very difficult. Okay, so this is what I wanted to like just demonstrate. Is that fine? Do you like roughly get what I'm trying to say here?
Yes, sir. Sir, can you print the singular values of the modified matrix?
Singular values of modified matrix. Okay, SVD, only singular values, right? And not print vectors. These are the singular values. Just a minute, it is taking time. Okay, my connection is gone. I'm using online MATLAB, so my connection is gone. I don't know. Yeah, here you get. So the smallest singular value is 0, and these are the singular values of TH.
Yeah.
Okay. The singular values of it's somewhere here. Here. These are the singular values. You made the last singular value 0, right? So you have the first 3 singular values preserved, and the last one becomes 0. Is that okay, Kaushik?
Yes, sir. Thank you.
Yeah. Okay, so this is all. This is all I wanted to say about low rank approximation. So thank you for your patience. I'm sorry I overshot time a little bit today, but that's okay. We'll continue this discussion tomorrow. Okay, thank you very much.